In our previous tutorials, we looked at how to design a bias network for an RF BJT, and then at how to make sure that this bias network is not affected by the RF source and RF load that we connect to the input and output of our BJT. To this end, we used some DC blocking capacitors which were self-resonant at the frequency of interest, which was 1.9 GHz. We also looked at how to avoid high-frequency signals flowing back into our bias network and eventually into our power supply, which would then modulate the collector bias and cause potential instability, inefficiency, and potentially exacerbating nonlinearities of our active device. Once all this was done, we then were able to measure the S parameter for our transistor, and then we are able now to use these S parameters to carry out the amplifier design. First of all, let's go back to our schematic and get rid of everything that we don't need anymore. So for example, we won't be needing the current and voltage meters into our bias network because we've ensured that there will be no RF currents flowing back into it. Of course, we need to keep the DC blocking capacitors and the RF chokes in our circuit. We can also just leave one schematic, the one with our bias transistors with all the safety elements in place, because we won't be needing them anymore for our amplifier design. I'm also going to delete all the graphs and then start from scratch with those as well. So we are now left just with the amplifier with a bias transistor, and what I'm going to do is add a graph. In fact, I will add one in a tabular form, and we'll call it S parameters. So we'll right click on this blank canvas, go to add a new measurement. We'll select complex as a format for our S parameters, and we'll start with S11 and then go to S21 and then add S12 as well, and then S22, and click OK and simulate. This gives us a full characterization in terms of S parameters of our two-port network. We can right click on this table now and go on to properties and change the display format to magnitude and angle. Click on OK. So now that we have changed the display format to magnitude and phase, this makes it easier to have an intuitive visualization of where they are roughly on the Smith chart. So through the S11, the input reflection coefficient, we can actually see the impedance that's presented by the amplifier at its input port. And also through the S22, we can see the impedance that is presented by the amplifier at its output port. The S21 tells us how much gain the transistor can provide in its present arrangement, and the S12 gives us an indication of how much power gets reflected back from the output back into the input port. It is very important to have a look at S21 versus frequency and see how its magnitude and especially its phase change across a frequency range. So since we're interested in both magnitude and phase of this quantity, the best graph that we can use is a polar plot. So let's just go to graphs, open a new graph and choose a polar plot, and then we'll call it S21 versus frequency. Now of course we need to go to project options and select a frequency range over which we want to see our S21. So let's start from a frequency of about say 0.1 GHz, and we'll go up to 4 gigs, and we'll do it in relatively large steps of say 0.2 GHz, and click on apply and then OK. Then we can right click on our polar plot, select add a new measurement, and we obviously want to see the S21 in its complex form versus frequency, so we'll just add S21 this way and click on apply and then OK. Then simulate. So at the lower end of our frequency range, the phase of our S21 parameter is around the 180 degree mark. So this means that the output signal is 180 degrees out of phase with the input signal. And this also means that if any feedback was to occur between output and input, if part of the output signal was able to couple back into the input, we wouldn't have a positive feedback effect, which may act as to increase the magnitude of our signals until our transistor burns out or it starts oscillating. We would have some kind of negative feedback, if anything. As we go up in frequency, the gain of the transistor diminishes in amplitude, and that is to be expected. If one looks at the model of a BJT, you can see that capacitances which are related to the transistor have a greater and greater effect, and hence they diminish the gain of the transistor. However, as we increase the frequency, although the magnitude of S21 decreases, the phase difference between input and output also decreases considerably. So now the output signal and the input signal have a much lower phase difference between one another, and hence if there should be some signal fed back from the output back into the input, then interaction could occur between these two signals, and perhaps oscillations could occur, and hence the transistor may suffer either in terms of its operation or in terms of failure. In fact, if we increase our frequency even further, so we go back to project options and select a stop frequency of 6 gigs, click on apply and OK, then simulate. So you can see that when we go up in frequency even further, the two signals, the input and output signals, are almost cophasal, and hence if there should be any signal from the output coupled back into the input, this could create a lot of trouble and create a positive feedback loop, and hence potentially either burn out the transistor or make it oscillate. The reason for looking at this is that we have to be very aware of what happens with the transistor gain, not just the frequency at which we're operating, but also at frequencies which are higher, and as we will see, lower than the transistor operating frequency. So now let's go back to project options and then revert to having one single frequency of operation of 1.9 gigahertz, and then simulate. And let's go back to our S parameters table. So we've seen that we have some sort of gain already available for us to use, but also if we look at the S11 and S22 in terms of their magnitudes, you can see that these are such that a lot of the signal that goes into this port is reflected back, which shows that there is quite a mismatch between our source and the input of the transistor, and our load and the output of our transistor. So one would assume that if we could reduce this mismatch through the use of matching networks, then we could increase the gain of the amplifier. And this idea, of course, seems to be quite sensible. So we might as well try to do that and see what happens. So let's start with the input of the transistor. The input of the transistor will have a specific impedance which is given by our S11 here. So through S11 we can actually work out, as we've seen in other tutorials, what the actual impedance that is seen at the input terminals of the transistor is. And we've also seen that to be able to achieve maximum power transfer, what we need to connect to this input impedance of the transistor is its complex conjugate. So we basically have to transform whichever impedance we have for our source into an impedance which is the complex conjugate of the impedance seen looking into the input port of the transistor. So how do we do this? Well, first of all, let's open a new graph, and this time will be a Smith chart, and we'll call it input match. So we know that the input port of our transistor has got an impedance which is given by S11, but the point we want to get to is the conjugate of this impedance, and this is not given by S11 but by its conjugate value. So we'll just right click on the chart, go on to add a new measurement, and then we'll pick S11 conjugate. Click on apply and then OK. Then simulate. So this is the point we want to get to. The impedance that we want the input port of our transistor to see is right here. And our starting impedance would be the impedance of our source, which is 50 ohm, right in the center of the chart. So the first thing that we need to do is, of course, change the appearance of a Smith chart, and we can just do this by right-clicking, going on to Properties, and then onto the Format tab. We can change the impedance lines to be green in color and the admittance lines to be red. Also, we can go on to Grid and then select the impedance and admittance grids to be displayed, take off the values and select the contour density to coarse. Click on Apply and then OK. Now I'm not going to go into this into great details because we've done this before in other tutorials, but it is quite easy in this particular case to carry out the match by using transmission line elements, an open circuited stub in shunt, and then a transmission line section. So let's open a new schematic. We'll call it input match, And then we'll put our starting termination, which is a 50 ohm resistor, which represents the internal impedance of our source, in the schematic first. So this is a 50 ohm source resistance. And then the first thing we add to this termination is a transmission line stub, which will take us down the constant conductance circle. So we'll put that in shunt with our termination, and we have to select its frequency to be 1900 megahertz. And also the electrical length, I'm not going to go through the calculation, I'm just going to tell you that it's 63 degrees. And then we'll connect this in. Then we can add a stretcher transmission line. This is the Tillene element, and we'll put it in series with the bit of matching network we've already got there. And then we again select the frequency to be 1900 megahertz, and the electrical length, yet again I won't show the calculation, but it's 75 degrees. Then we can put a test port in to see the new impedance that we've transformed our 50 ohm load into by using this matching network, which comprises of a shunt, an open circuited stub and a transmission line. And we can display it on the Smith chart and see that it matches what we wanted to get to. So let's go back to input match, and then we'll add a new measurement now. We'll add S11 coming from the input match, because this is the one we want to see. And make no mistakes, this time we don't need the conjugate, we actually want to see the actual impedance presented by that network. So we need to revert to complex. Click on apply and then OK. Let's move the legend out of the way and then simulate. And you can see that now we've got the two impedances matching perfectly. So we started from 50 ohm here, and then we used an open circuited stub to go down the constant conductance circle. Then we used a transmission line section to move around a circle centered on the center of the Smith chart up to the termination we wanted to get to. So now, instead of the 50 ohm source impedance, what we're seeing from the input terminals of the transistor is the conjugate of its own input impedance. And because now what the transistor sees at its input terminals is the conjugate of its own input impedance, then we should have maximum power transfer. Now we can go back to the input match schematic. We need to flip this network over somewhat, because of course the 50 ohm source impedance should be on the other side. So we can just select everything here, and then right click and select flip, and then draw the line about which we want to flip the circuit. And there we have it. So this represents our 50 ohm source impedance. Then there is a matching network here which transforms this source impedance into what we see at this port here, which is the conjugate of the input impedance of the transistor. Now we can just copy these two bits by pressing Ctrl C, and we can go back to our schematic and insert them at the input of the transistor. Let's remove some of the connections here, press Ctrl V, and then we can put our matching network in and then reconnect everything together. Now let's simulate, and let's go back to our S parameters. You can see that your S11 measurement has actually gone down quite a bit. It's gone from being 0.7 to being 0.04 roughly in magnitude, which means that you've got really quite a good match at the input of the transistor. And you can also see that the gain has gone up quite a bit. I mean, we had a factor of 5.4 earlier, and now we've got 7.5. So you may say, well, splendid, that seems like a great thing to do. What about matching the output now to make our gain even greater? And this is when you go and have a look at things and you get a nasty surprise. Now you can see that the output reflection coefficient has actually gone to a value which is greater than 1. This is really bad news, because it means that the reflective power is greater than the incident power. So this can only happen, of course, when you have an active device. That means that any power that goes into port 2 gets amplified and reflected back with even greater magnitude. So this is not good, because this means that you may create oscillations, that your transistor is unstable. So we can see that we can't just do things in a simple way with a transistor. There is always some level of instability with the transistor that has to be sorted out before we carry out our design. So what we want to avoid is having reflection coefficients, both at inputs and outputs, being greater than 1. because this is bad news for the transistor. It can create oscillations or even destroy the device. So we need to make sure that whatever terminations we put at our input, they don't actually make our output reflection coefficient go over 1 in absolute value. And equally, we don't want to put terminations at the output which make the reflection coefficient at the input be greater than 1. And we will be seeing shortly how we can select the right terminations by using stability circles, which give us an indication of what terminations are safe to use and what terminations can potentially cause oscillations. But how do we work out if our transistor is indeed unstable at the frequency at which we're operating? Well, let's go back to our schematic and get rid of this matching network here so we can revert to having the S parameters just as we did before. So let's resimulate and then go back to our S parameter table. So now we've come back to the situation that we had before. There is a specific measure that you can display in Microwave Office which will tell you whether your transistor is potentially unstable or not across a specific frequency range. So let's just take a look at that. Let's go to Graphs and then New Graph, and then we'll choose a rectangular graph and we'll call it the mu factor. And then we right click, go on to Add a New Measurement, and then we can go to Linear Measurements and Stability, and you can see here that you've got two stability factors, mu1 and mu2. These two are calculated in a similar manner, so they pretty much represent the same thing, and if one shows instability, so does the other. But we'll display them both to begin with, just to show you how similar they are to one another. So let's choose mu1 first. Of course, we want it to come from the S parameter measurement schematic, and click on Apply. And then we'll choose mu2 and click on Apply, and OK. As we pointed out, we can't just look at the stability of our transistor at a frequency of operation, because as you've seen earlier, as you increase the frequency, instability can really set in, and if you had a broadband signal coming into your transistor, you'd have to be aware of what can happen. So let's go back to project options, and we yet again select a broader frequency range, say 0.1 gigs to 4 gigs. And we can reduce the step here to 0.1 gigs to make it a bit finer. Click on Apply and then OK. Then simulate. Now you can see the mu factors, and you can see that they have a really pretty similar shape, and hence you could just use one of them. The one that's most commonly used is mu1. So to have a transistor that is unconditionally stable, that is, whatever terminations you connect at its output or input, you can't make it oscillate. You have to have a mu factor which is greater than 1. We can clearly see that here this is not the case. So around the frequency which we're operating, which is around here, we are way below 1, and hence there are potential instabilities. This doesn't mean that the transistor is always unstable. It only means that there exist some input terminations and some output terminations that can make the transistor unstable by making either reflection coefficients greater than 1. So I'm going to get rid of one of the two mu factors. I'm going to get rid of mu2 because we don't need to have two measurements on here. Let's just keep the mu1, which is the most common one. And now we'll have a look at what input terminations can cause the output reflection coefficient to be greater than 1, and what output terminations can cause the input reflection coefficient to be greater than 1. And of course, because we're looking at value of impedances, we can just use the Smith chart to represent these, with very useful tools which are called stability circles. So let's go back to Graphs and then open a new graph. It'll be a Smith chart because we want to represent a set of impedances, so this seems to be the most obvious choice, and we'll call it stability circles. Now let's right click on the chart and select Add a New Measurement, and then under the Linear section we'll select Circle. Now we've got two types of circles, represented by SCIR1 and SCIR2. So SCIR1 gives you input stability circles. What these are circles which will show you which region of the Smith chart contains terminations that, if connected to the input port, will make the output reflection coefficient be greater than 1, and hence the transistor potentially unstable. The SCIR2, so the output stability circles, will show you which region of the Smith chart contains terminations that, if connected at the output of the transistor, will make the input reflection coefficient greater than 1, and hence, yet again, the transistor potentially unstable. So we'll add both of these measurements to our chart. So SCIR1, input stability circles, from the S parameter measurement schematic, because these are calculated using the S parameters. Click on Apply. And then SCIR2, which is the output stability circles, and again from the same schematic, click on Apply, and then OK. Now, to make things easier for now, let's just go back to project options and select one single frequency as our frequency of operation. So we'll just look at the stability of our transistor at our frequency of operation to begin with. So let's click on Simulate. Now you can see the stability circles and how they intersect the Smith chart. Let's start with the input stability circle SCIR1, which is shown in blue on the chart. This input stability circle splits the chart in two parts. On one of these two parts, the simulator has also drawn a dashed line. Now, this part with a dashed line in is the part that contains all the terminations that, if connected to the input of your transistor, would make the output reflection coefficient of your transistor greater than 1. So what we can do is plot on this chart the impedance that we connected to the input terminals of our transistor earlier, and which we saw made the output reflection coefficient of the transistor greater than 1, and see if this impedance is actually contained in the unstable part of the input stability circle. So let's just right-click, go on to Add a new measurement, and then we'll choose port parameters, S11, which is what gives us the impedance, and this will be the S11 seen for our input match schematic, which is where we had the input matching network, and hence it will represent the impedance that we connected to the input of the transistor. Click on Apply, and then OK. Now you can see exactly where it is, and you can see that this termination is in the part of the Smith chart which the input stability circle shows as containing all the input terminations that would make our output reflection coefficient greater than 1, and hence the transistor unstable. So you can see how this actually ties in well with what we did earlier. So we can just remove this point now, because we've made a point we wanted to make, and go back to our stability circles. Ideally, what we want to do is push this input stability circle out of the chart completely, so it doesn't intersect it at all. And in that case, if the input stability circle is completely outside the chart and there's no intersection, then we basically are safe to choose any terminations for the input, because none of them will make our transistor unstable. For the output stability circle, we have a similar situation. We've got the output stability circle splitting the chart in two parts, and then Microwave Office tells us that the part which has got the dashed line inside it is the one that contains the terminations that, if connected to the output ports of our transistor, will make the input port reflection coefficient greater than 1, and hence the transistor unstable. So ideally what we want to do is push these two circles outside the chart, and then we will not have any terminations on the chart that we could possibly choose that will make the transistor unstable. And if we manage to achieve this, what we have achieved is unconditional stability for our transistor. That means that no matter what you connect to it, then you're never going to be able to make the transistor unstable. And that's a great position to be in. It's a very safe position to operate. So how do we make our transistor unconditionally stable? Well, this can be done by adding series resistors or shunt resistors to the input and or output of our transistor. To illustrate how this works, I'm going to put together a little schematic which will help us gain a bit of an insight into how this works. So let's go back to Circuit Schematics and open a new schematic. We'll call it Resistive Stabilisation, and then we'll put a simple port in there by pressing Ctrl P, and then an impedance element, imped. So we'll just press Ctrl L, type imped, and place the element on the schematic like so. Then we get ourselves a ground, and we put it on one side and connect the other side to our test port, so we'll be able to see the impedance of our element. Now we'll set the resistive part of our impedance to 10 ohms. And in terms of the reactive part, we are going to set up a swept variable which will allow us to represent different impedances on the same constant resistance circle. So we've seen how this is done in previous tutorials. We'll just get ourselves an equation and we'll set up a variable called XS and give it an initial value of 0. And then we'll press Ctrl L and we'll get ourselves a swept variable control element, place it on the schematic. The variable name will be the name of the variable we've just inserted in our schematic, XS. In terms of values, we'll set up a range by using the stepped syntax. And so we'll just type stepped and then put in the minimum value, which we'll say is -100, the maximum value, which we'll say is 100, and then the increment, which we'll say is 15. Lastly, we will assign this swept variable XS to the reactance of our impedance element. So now let's go back to our Smith chart and we'll add a new measurement. It will be again the S11, which comes from our resistive stabilisation schematic. So we can see the impedance of the imped element that we've got on the schematic. Click on Apply and then OK. Now simulate. And you can see that what I've got is a number of impedances all on the same constant resistance circle. And this is just what we did. We set the resistance of the impedance to a fixed value, and then we swept the value of the reactance so as to have a number of impedances plotted on the Smith chart which have the same resistive value and varying reactance. Now you can see that a number of the impedances plotted on this chart are actually inside the unstable part of the input stability circle. And that means that if your transistor saw any of these impedances from its input terminals, then the reflection coefficient at the output would be greater than 1, and hence you would have instability. So how do we ensure that our transistor never sees the impedances that are contained in the unstable part of our input stability circle? Let's go back to our resistive stabilisation schematic and make the resistive part of our impedance element tunable. Then let's go back to the Smith chart, open the tuner, and then set the range for the resistive part of our impedance to be between 0 and 50. Now, if we slide the tuner down to 0, we can see that for impedances that have a 0 resistive part, there is a possibility, depending on the reactance, that we might be inside the unstable part of the input stability circle. Now, as I increase the resistive part of my impedance, you can see that I still have some impedances, depending on the reactance, that are inside the input stability circle. So I carry on increasing it and increasing it until none of the impedances is inside the unstable part of the input stability circle. So you can see that if I have an impedance with a resistive part which is greater than 29 ohms, then irrespective of the reactive part of this impedance, I can't possibly be inside the unstable part of the input stability circle. This means that if I put a 29 ohm resistor directly in series with the input of my transistor, then no matter what terminations I connect on the other side of this resistor, I will never end up in the unstable region of the input stability circle, which gives me unconditional stability, at least from the point of view of the input terminal. So let's just go back to our schematic and verify this. Let's put a resistor in series with our impedance here, connect it to the test port, and give it a value of 29 ohms. Then let's go back to our Smith chart and click on Simulate. Now you can see that if I decrease the value of the resistive part of the impedance element to 0, I'm still going to remain into the part of the Smith chart which contains the terminations for which the transistor is going to be stable. Of course, if I increase the value of the resistive part even further, then I'm going to move further and further away from the boundary between stable and unstable terminations determined by the input stability circle. But the important point here is that by putting a 29 ohm resistor in series with my input, I've been able to end up in a situation where no matter what termination I connect at the input, I will never make my reflection coefficient at the output greater than 1. So let's close the tuner and let's get rid of this schematic that we put together, and let's get rid of this measurement as well, of course, and simulate again. Now what we can do is go back to our actual schematic here and put the 29 ohm resistor right there in series with my base and see what happens. So I'm going to connect our resistor in series with the base, put a 29 ohm resistor there, and then simulate and go back to the Smith chart. Well, look at that. You can see that now you've pushed both your input and your output stability circles completely outside the chart. And this is something that often happens. You actually sort out the stability at one port, and then the other port as well ends up being stable. So you can see that you've got the input stability circle there, and the unstable region is on the inside of it, and there's no intersection with the Smith chart at all. So all the terminations of the Smith chart, both at the input and output, will never determine the input or output reflection coefficients to be greater than 1 in absolute value. Now let's look at other ways to stabilize the transistor. So let's get rid of this 29 ohm resistor here and go back to our original state. And then let's look at our Smith chart again. With resistive stabilization, you usually have two options: either adding a resistor in series with your port or in parallel with your port. Now there are limitations there. For example, in the case of the input stability circle, one of the unstable terminations is a short circuit, and you can't really use a shunt resistor to stabilize the transistor when a short circuit is connected to it. So you can only use a series resistor to stabilize the input in this case. For the output, however, you do have the option of either adding a resistor in series or a resistor in parallel. So to find the value of the resistor that we need to stabilize a port with a series resistor, we need to find the constant resistance circle that's tangent to the circle of interest. So in this case, the output stability circle. And we can do that quite easily in Microwave Office by just adding a marker, pressing Ctrl M, and then clicking on the output stability circle. We can also change the readout to be denormalized, so I'll do that quickly. Go into Properties and then Markers and choose to be denormalized to 50 ohms. That way you can see the value of the resistor directly. And then you can move your marker until you find the maximum value of the resistive part of the impedance which is encountered along this circle. So if I move my marker up and down a little bit, I can see that the top value that I get is around 64.8. So I can basically just say that if I put a 65 ohm resistor in series with my output, then I will be able to get a stable transistor. So we can just do that and verify it. Go to the S parameter measurement schematic, and then let's make a little bit of space here so we can insert our resistor in series with the output. And we said we wanted a value of about 65 ohms from our marker readout. Then click on Simulate, go back to the Smith chart, and you can see that yet again we've achieved what we set out to achieve. Now lastly, let's go back to the schematic and get rid of this resistor. And let's have a look at what other configurations we can use to stabilize our transistor. Now so far we've only used series resistors, but now let's see if we can do this with a shunt resistor at the output. We've seen that in the case of the input we can't use a shunt resistor because the short circuit termination is one of the unstable ones. But at the output we can. So what I'm going to do is just right click on the chart, go on to Properties, change the marker readout to admittance because it's easier to do it that way if you're adding a shunt resistance. And then we can go to Grid, and we don't actually need the impedance grid or any values for that matter. We just use the admittance grid and then click on Apply and OK. So in this case we need to find the constant conductance circle that's kind of tangent to our output stability circle. And again we can use the marker to our advantage. We can just move the marker up and down until we find the kind of maximum conductance that we can possibly find. And you can see that the maximum conductance is around 9.1 millisiemens. So effectively you are looking to add a resistor in parallel which has a conductance of 9.1 millisiemens. If we convert that into ohms, we can work out easily that this is a shunt resistor of 110 ohms. So I can go back to my schematic, and add a resistor in shunt with the output with a value of 110 ohms. So now there is one fundamental difference between adding a resistor in shunt and adding a resistor in series. When we had the resistor in series here, there was no DC bias current that could flow through it, because here there was a DC open circuit. So there was no current path for the DC current to come through our series resistor, and hence there was no problem at all with it affecting the bias. But in this case, if we connect this resistor directly to ground, there is a problem, because we would have some of the DC bias current flowing down this resistor instead of going into the collector. And this is of course a problem. But what we can do is just use a simple capacitor, the same that we used as a DC blocking capacitor for our output port, and this way the stabilizing resistor will have no effect on our bias circuit. So let's just click on our capacitor here, press Ctrl C and Ctrl V, and then we'll just place it in series with our resistor here, and then connect a ground at the end of it. Now click on Simulate, and then let's have a look at the stability circles yet again. You can see that now our stability circles, again, are both out of the Smith chart, so the whole chart, all the terminations on our Smith chart, will be terminations that, if connected to the input or output of our transistor, will not make the reflection coefficient at the other port greater than 1.